Hello, this is a brief presentation on independent samples T. Well, maybe not so brief, but it's a presentation on independent samples T. So we have two sample examples. We already had a lecture on dependent samples T, but now we have two sample or independent sample T's or unrelated samples. So we have males versus females, curves versus Nutrisystem, or P90X versus Pilates. There's a exercise theme, I guess, going on right now. But you can have a whole slew of other examples. So one reading program versus another. You could do several things with this, but it's basically independent samples T versus dependent samples T. So we have two designs for two samples. So independent measures or between subjects designs. So example males versus females, where there are two distinct separate samples. So meaning not husband and wives, if you're thinking of the dependent samples example, but two distinct separate samples. And actually in the independent samples design, you would remove anybody who was, couples, who were both in the study, because you wouldn't want that to interfere with your assumption of independence, which is an assumption of parametric tests that observations would be independent of one another. And this is what we're going to be talking about today. There's also repeated measures or within subjects designs, which there's a lecture online about that I did regarding dependent samples T or related samples T. And the most common example is pre-test versus post-test. And where one sample is measured twice, creating two related samples. This is also called dependent, paired, or related samples T. So there's a couple different terminologies for that. There seems to be more terms for this one than the independent samples T. But today it's all about the independent samples T. So independent measures T. To calculate independent sample or measure T is not all that different, except now that we have two means, because it's two distinct separate samples versus the dependent samples where it was basically treated as one big sample, two sums of squares, and two ends. And so how do we state our hypotheses? For the null, we state H sub O or H subscript O mu sub 1 minus mu sub 2 equals 0, saying that there's no difference in the population means. For the alternative, we state mu sub 1 minus mu sub 2 does not equal 0, saying that there is some sort of mean difference. So how do we calculate our T? Same basic T structure as before, sample statistic minus hypothesized population parameter. So that's whatever you ascribe in your hypothesis. In our case, or most cases, it's 0, the null. And then over the estimated standard error. So where one sample mean is to test a hypothesis about one population mean, now we have two sample means. So an independent samples T for two sample means that the sample mean difference minus the population mean difference over the estimated standard error. In other words, mean sub 1 minus mean sub 2, as being the sample mean difference, minus mu sub 1 minus mu sub 2, which is the population mean difference, over the standard error for the mean sub 1 minus the mean sub 2. The numerator is simply the mean differences. This is pretty intuitive to understand. So the denominator is estimated standard error, which is a bit different than in the dependent samples T. And the calculation is also a bit more tedious, but that's okay. So what's this new standard error about? So for two samples T, or two independent samples T, we have two means, and each mean is going to approximate mu with some error because they're independent samples. We're not talking about one sample anymore, we're talking about two independent samples. So mean 1 is going to approximate mu with some error, and the mean 2 is going to approximate mu 2 with some error. So we calculate an overall estimated standard error with the following equation, which is the variance of one variance sub 1 over the n sub 1 divided by n sub 1 plus the variance sub 2 divided by the frequency or the number sub 2 sample size over square root of that whole function. Weight, this calculation though is limited to where there's two equal sample sizes. So intuitively you would think, oh, that's it. But that assumes that there's two equal sample sizes for the equation above. So it gets even a little bit more complicated because we don't always have two equal sample sizes for each group in independent samples T. So what about unequal ends? Well, we have to calculate the pooled variance, which is notated as S squared sub p, which equals sums of the squares sub 1 plus sums of the squares sub 2 over degrees of freedom sub 1 plus degrees of freedom sub 2. Then we calculate our estimated standard error, which is the estimated standard error would be the S sub 2, and that's basically the pooled variance S2 pooled plus S2 pooled over n sub 1 plus n sub 2, then take the square root. And notice that's the same pooled variance value used each time, but you would have a different n1 value and a different n2 value because it's about unequal ends. If you don't do this, your standard error will be biased, and therefore you might not end up rejecting the null when you should. So it's very important that you get the correct estimation of standard error. So what's the DF? What's the degrees of freedom? So let's examine our formula. In calculating the estimated standard error, we have two sample statistics, so which we assume represent population parameters. Okay, so in two related samples T, we only assumed that we were talking about one population parameter because they're two related samples. But now we have two independent samples, and we're saying that we're approximating two population parameters. Thus, we get this, we have n minus 2 versus n minus 1 in this case. But basically m sub 1 and m sub 2 in calculating s squared 1 and s squared 2, or sum squared 1 and sub squared 2. So, in short, we lose 2 degrees of freedoms in an independent samples T test versus 1 in a dependent samples T test. So, important to know. And so, in this case, we can state that degrees of freedom equals degrees of freedom sub 1 plus degrees of freedom sub 2. So, degrees of freedom for sample 1 plus degrees of freedom from sample 2, which can be alternatively stated as n sub 1 minus 1 plus n sub 2 minus 2, or total n minus 2. So let's talk about a hypothetical example with some data. A psychologist is studying mental images and memory. The psychologist prepares a list of 40 noun pairs, like dog and bicycle, grass and door. And one group is given this list instruction just to memorize it. Another group is given this list instructed to memorize it specifically using mental imagery or mental images to associate it. So like literally visualize a dog riding a bicycle. And this is the following data that were achieved from this study. So you have group 1 who was instructed to think of imagery, and then group 2 that was instructed not to think of any imagery. And we have the n equals 10 for each group, and then we have the mean of 26 for group 1, and then a mean of 18 for the second group, and then the sums of square of 200, and the sums of square of 160. First, we need to state our hypotheses respectively, null and alternative. H sub O is mu sub 1 minus mu sub 2 equals 0, which would suggest that there's no difference and that imagery has no effect on memorization ability or recall ability, because what we're really talking about is recall here. Then we have H sub 1, our alternative is mu sub 1 minus mu sub 2 does not equal 0. So imagery produces a difference of some kind. And we can go ahead and set the alpha at 0.05, which is quite typical. And then we can find our critical region. To find our critical region, we need to ask ourselves some questions. One, is this a directional or non-directional test? This is definitely a non-directional test because we did not ascribe a directionality in stating our hypotheses. Next question is, what are our degrees of freedom? In our case, we have n sub 1 is 10 and n sub 2 is 10. So 10 plus 10 is 20 minus 2, because remember we're approximating two population parameters, so that would be 18 degrees of freedom. And so what's our T critical value? Look it up on a chart. There's a chart in the back of Field, but there's also several charts that you can find just are widely accessible in the back of most introductory statistics books. And just online, just type in T chart. But anyway, so for degrees of freedom 18 at an alpha 0.05 for 2-tail T, it looks like our T critical value, or our T sub V sub CV, is a 2.10. Okay, so that's the critical value that we need to exceed in calculating our T test statistic. So let's calculate our T, and I highlighted the means there. So you have the means of 26 minus 18 minus 0, okay. So that'd be 8 in the numerator. And then we have the estimated standard of error of 2. I'm skipping ahead. We'll go back to the standard error. So that gives us a T value, or a T test statistic value of 4.0. Now we compare the test statistic value to the critical value. Remember, our T sub CV was 2.10. So did we exceed the critical value? Definitely, because a T tested C critical value of 2.10 is less than a test statistic value of 4.0. So we are definitely in our critical region there. But wait, how did you get that estimated standard error? Remember, we first have to calculate our pooled variance. So our sums of squared for the first sample plus the sums of squared for the second sample, divided by the degrees of freedom for the first sample plus the degrees of freedom for the second sample. So that's 200 plus 160 over 9 plus 9, so 360 over 18, which could give us a pooled variance of 20. And secondly, we use that pooled variance to compute the estimated standard error. So in this case, so 20 plus 20 over 10 plus 10 square root, which would boil down to 2 plus 2 square root, which would be square root of 4, which is 2. So that will give us the estimated standard error there. So it's easy to do, but you have to make sure you do the right steps. The math is simple, but it's a little tedious, so make sure you don't get lost in it. So do we reject the null? Yes, we do, because our T test statistic value was 4 something, 4, and yes, it was 4 exactly. And that exceeds the critical value of 2.10. So we can reject our null hypothesis in this case. And what does rejecting it mean? It means that there's probably some effect of using mental imagery to recall different noun pairs like dog and bicycle. So do mental images increase accuracy and memory? It appears to do it, appears to be that appears to be the directionality of it. But we want to know by how much. So to do that, we calculate a Cohen's d. In this case, it's adjusted, the Cohen's d. So it's the same numerator, mean sub 1 minus mean sub 2, mean differences, over the square root of pooled variance. So it's basically pooled standard deviation. And in this case, we have mean sub 1 minus mean sub 2 is 26 minus 18, which gives us the value of 8. When our pooled variance was 20, so square root of 20 is 4.47, so 8 over 4.47 is 1.79. And that's a pretty large t-value, 1.79. Yeah, I just answered my own question. But it's a pretty large d-value. So any d-value above 0.80, I know if I said this already a couple times, 0.80 is large. So more on effect size. You can also calculate an R-square from using the t-test statistic value, not the critical value, the t-test statistic value that you calculated, not the critical value from the chart. So t squared over t squared plus degrees of freedom. So for this example that we just discussed, so 4 squared over 4 squared plus 18, so that's 16 over 16 plus 18, which is 16 over 34. Gives you a resulting R-squared value of 0.47, which I would consider quite large. Yeah, so it's saying that 47% of the variance in recall may be accounted for by the use of mental imagery. We can also do directional hypotheses. In performing directional, does our alpha level change? No, it does not change. What's going to change is it's going to change what column you read on the chart for what is your critical value. And does our t critical value change? Yes, that's what's going to change, because it depends what column you read now based upon the alpha. But you wouldn't change your alpha just because it was directional. Okay? Okay, that was a brief presentation on independent samples T, and good luck.